to the lecture series on complex analysis for undergraduate students. Today's lecture is on Cauchy's integral formula. Last lecture we have done the Cauchy integral theorem. The main consequence of Cauchy integral theorem is Cauchy integral formula. This formula is very helpful in evaluating the integral, but equally important is this formula in having an important role in proving certain results of the analysis. It helps in proving that analytic functions have derivatives of all order. It helps in proving the Taylor's expansion of any function. Moreover, it is helpful or it gives the proof of fundamental theorem of algebra. So, let us see what is Cauchy integral formula. But to find out the Cauchy integral formula, first we have to extend our Cauchy integral theorem to multiply connected domains. We have done the Cauchy integral theorem for simply connected domains. We have to extend it to the multiply connected domains. But for the multiply connected domains, we require it to prove that it is only on the boundary of the multiply connected domain, while Cauchy integral theorem was holding true for any closed simple closed contour of the simple domain. For multiply connected domain, we will stick only to the boundary. Let us see the Cauchy integral theorem for multiply connected domain. The statement, let C be a simple closed contour and Cj for j is equal to 1 to p be finite number of simple closed contours inside C, such that the region interior to each Cj has no point in common, and let R be the region consisting of all points within and on C except those points which are interior to each Cj, and let B be the boundary of this region R. In other words, what we are saying is that let R be a P connected domain with boundary B and F is analytic in R, then integral of Fz along this boundary B is 0. What we are trying to say is, let us see with the help of a figure. This is a domain, multiply connected domain, you see. We do have here for example, these 4 holes. So, this is a 4 connected domain, let us say. What we are having is one boundary, outer boundary C, and then we do have, so we do have a simple closed contour C and another contour Cj's, finite number of simple closed contours Cj's. Here I have taken them elliptic one, they could be of any form, but closed contours Cj's, such that each of these Cj's does not have any point in common, and moreover they are interior to this interior of this contour C. Then we say is that the boundary will consist of this C, C1, C2 and so on, all the Cp. So, if I take up the boundary in sense that all the interior points means the interior points of these each of these Cj curves that we have to take out, so that it is a multiply connected. So, we take that this orientation of the outer boundary C is the counterclockwise, while as for all the inner curves Cj's it is clockwise, so that the interior points are all left to the boundary. Then we say is that if we take the boundary in this sense, then along this complete boundary, that is this plus C1 plus C2 and so on, this would be integral of analytic function would be 0. This is what is extension of your main Cauchy theorem, which says is that along any simple closed contour in simply connected domain, integral of Fz along that contour C is 0. We are having it on the boundary. Let us go to the proof of this. For proving this, we would see it one by one, that is first we will go with the doubly connected domain. Let us see, this is a figure of doubly connected domain. We have this outer boundary C and this inner boundary C1. Now, for proving this in the doubly connected domain, what we will do is we will first make this divide this domain into two parts. The divide is with these through these two cuts, one is this L1, another is L2. So, in this one what we do say is we want to prove that integral along this boundary is 0. So, now if I do take our simple definition of any closed contour, the orientation is always counterclockwise, then what we say is this integral along this boundary C plus integral along this boundary C1 in this manner is 0. What it says is we want to claim that integral along this boundary C is same as the integral along this boundary again in the counterclock manner, C1 is same. This is what we want to show. So, we have divided this into two domains now. So, now see the upper domain from this part, this is D1 and this lower one. Now, you see this upper one, this is now a simply connected domain, this is a simply connected domain. Similarly, this is also a simply connected domain. So, what we have done, we have divided this doubly connected domain into two simply connected domains D1 and D2. Now, in simple connected domain the Cauchy integral theorems holds. So, let us see how we are going to do is in D1 the simple closed contour I am taking the boundary of this domain. This is of course, so we would start this boundary like this one L1 C, the upper part of the C, then L2 and then this upper part of C1. This is a closed contour in the simply connected domain D. So, the Cauchy integral theorem holds true. What it says is integral along this closed contour should be 0. So, let us write it out L1 Fz dz plus C star is this upper part of C plus L2 Fz dz plus integral along this upper part of C1, that is I am writing it C11 star in this clockwise manner. So, this is should be 0. Similarly, if I just go in D2, now in D2 the orientation of this boundary I would take in this manner where this red orientation we had shown. I would start from L2, that is from this point L2, then this portion of C, then L1 and then we will go in this manner. So, we will complete the complete boundary. So, in D2 if I write L2, that is it should be minus L2 because L2 we have taken this direction. So, when I am taking the integral along this direction it should be minus of L2. So, minus of L2 Fz plus C star star, that is the orientation is again the counterclockwise of the C, the lower half portion of the C, that is C double star Fz dz plus minus of L1 because L1 is in this direction. So, this is minus L1 and then C1 2 star, that lower portion of this C1 curve in this direction. This should also be 0 because D2 is also simply connected domain. Now, if I add these two, what I would get? You see, I am adding this boundary and I am adding this boundary. So, see, once I am adding L2 from this direction, then I am adding the L2 in the negative direction. Since Fz is analytic and it is simply connected domain, we do know that it is independent of path. So, integral along L2 and minus L2, that should be negative of each other, or that you could say is that is since reversal one it will give the same one. So, I would get this L1 and this minus L1 and this L2 and minus L2, they would get it, cancel it out. Then the C star and C double star. C star is this oriented curve and C double star is this oriented curve. If I add this up, what I do get? Complete C. Similarly, C11 star is this oriented curve, while a C12 star is this oriented curve. So, when I just add it up, I would get this as C1 in the clockwise manner, that is in the negative sense you could say. So, if I write it out in the sense reversal form, that is if I change the orientation, it should be minus of C1, or that is this minus of C1, this is what is the clockwise manner. In counterclockwise manner I would call it C1. So, if I add it up, what I would get? C Fz dz plus minus of C1 Fz dz is equal to 0. So, from here if I just write it out, it should be C integral along the contour C of Fz dz is same as minus of integral along the contour of minus C1 Fz dz. So, we call it equal to that using the sense reversal one, that is it should be equal to the contour integral along the contour C1 fz dz. So, what we had proved that this is true, and if I C is here, this is what the theorem says is that the complete boundary, the boundary is C and C1. So, this is the complete boundary. What we are having is integral along the complete boundary B of the function fz dz is 0, and this says is that integral is same, or rather you could say is that is again we have established the independence of path on the closed contours in multiply connected domain. That is, if either I take this path or I take this path, the integral along both these contours would remain same for multiply connected domain for analytic function fz. Now, this is we have done for the doubly connected. Let us extend this to the triply connected, and then it would be clear that is it could be unepi connected domain. So, let us see this figure for the triply connected. So, we do have two holes here, or you could say is the three boundaries. So, we do have this is a triply connected domain. This particular shape of the domain I have taken in this manner. You can take in any other manner, but in the sense that is you could divide it into two simply connected domains. That is how we have to just think about, and that is possible for every triply connected domain. So, we have coming as this triply connected domain. We are introducing here three cuts L1, L2 and L3. By these three cuts, you see I could divide it into two domains. One is this upper domain, you see from this side I am just telling you L1, L3, then this upper portion of C1, then L2, then upper portion of C2, like this. This is upper domain, this is a simply connected domain. Similarly, I do have another one, this L1, lower portion of C, and then this L3, then this lower portion of C1, then L2, then lower portion of C2. We are having this is another domain D2, both are simply connected domain. So, again in the manner of in the doubly connected domain I have done, we would just go in the similar manner for here. So, let us first consider this domain D1. Here the simple closed curve I would take starting from here this complete boundary. So, what we do have L1, then upper portion of C, this is C star I am denoting. So, integral along this of the analytic function f. So, C star fz dz, then L3, then upper portion of C1 in the clock manner, that is in the negative sense. So, integral C11 star, C11 star is this directed path, then L2, and then we would have C21 star. So, we are having this complete boundary L1 C star, L3 C11 star, L2 and C21 star. Along this the integral of fz dz, that should be 0, because this is a simply connected domain and this is a closed contour in the simply connected domain. So, it should be 0 according to the Cauchy integral theorem. Now, in the similar manner I will take the boundary of the D2. Now, for boundary of the D2 I would start from here. We just go this L3 in the negative direction, then the lower portion of C in the counterclockwise manner, then L1 again in this negative direction, because L1 we have defined the direction is from this side to this side, then C2 in the negative sense again, L2 in the negative sense, and C1 again this negative sense. So, let us just write it out. In D2 we do get it minus L3 C star star, that is the lower portion of C, then minus L1 lower portion of C2, that is we are writing C22 star, then minus L2, then lower portion of C1, that we are writing C12 star. Now, this is the complete boundary, this is a closed curve. So, because of Cauchy integral theorem, in the closed contour this integral must be 0. So, this whole integral should be 0. Now, if I add these two, what will happen? You see again here we are having is L1 integral of fz along the path L1, as well the integral of fz along the path minus L1. You see here we are having is once we are moving this side, another time we are moving from this side. So, when we add it up both these two things, I would get it simply 0, that is whatever this integral, that would give me 0. Similarly, for all these cuts L2, once we are moving to the positive orientation, another we are moving in the negative orientation, then for L3 also in the similar manner. So, all these cuts we would get them 0. What is being left is, that is these paths we are having is upper half and lower half. For C we do have upper half and then the lower half in the same direction. So, it will add up to give me the complete C. Similarly, for C1 we are moving to the upper half in this negative sense and then the lower half also in the same negative sense. So, this add up will give me the complete boundary C1 in the negative sense. Similarly, the complete boundary of C2 we would also get in the negative sense. So, what we would get actually, we would get that integral of fz along the boundary C plus integral of fz along the boundary C1 in the negative sense. So, I am writing it as minus C1 and plus integral of fz along the boundary C2 in the negative sense. So, we are writing as minus C2. You see is that is I am always using here is negative sense and positive sense. This I have made a convention, that is whenever it is a simple closed contour, we would call the counterclockwise direction as the positive sense and the clockwise direction as the negative sense. That is how we are writing it out. So, this is equal to 0, that says is this is the complete boundary of the this triply connected domain. So, we have shown the result over here, but from here we are getting another formula, that is integral along this outer boundary is sum of the integrals along the inner boundaries. So, what we are having is integral along C of fz dz is integral along C1 fz dz plus along C2 fz dz. That is what we are saying is that if it is a, in general now we could show that is in similar manner, if it is a p connected domain, then on the complete boundary the integral of an analytic function would be 0. What it says is that the integral along the outer boundary will always be same as the sum of the integral along the inner boundaries. This is what is the extension of Cauchy integral theorem in multiply connected domain. Now, let us see how this is helping in evaluation of the integral first and then we will see that Cauchy integral formula. So, let us see one example. Evaluate this integral dz upon z square into z square plus 9 along the boundary B, where B is the boundary of this given region, that is this is the disk from z mod z is lying between 1 and 2. This is the disk. Along this boundary we have to show that the integral of this function is we have to evaluate. You see this function is not analytic at z is equal to 0 and z is equal to plus minus 3i. You see z is equal to 0 is the origin, plus minus 3i they are here. The disk and the reason on the boundary what we are having is the boundary is of this disk, that is outer boundary and this inner boundary in this negative sense. So, both these points of where this function is not analytic, they are outside this region. What we do conclude is that this function is analytic except at the point 0, 3i and minus 3i, and all these 3 points are lying outside the given region. So, what we are having is my given function f z is analytic in a doubly connected domain. That says is that Cauchy in theorem for multiply connected domain says is that along the boundary of this doubly connected domain the integral must be 0. Hence, this integral along this boundary should be 0. Now, let us do one more example where that example is of an importance just because you see is that is we would be using that example in finding out many important results. So, let us move to another example. Evaluate this integral, this is simply your 1 upon z minus z naught, or we are writing it as z minus z naught to the power minus 1 dz, where this boundary B is of this domain. You see again this is a doubly connected domain, you find it out. We are having is this boundary B is completely outer one as well as this inner one in the negative sense. That says is boundary is now I am taking at the two sets. One is this outer boundary, that is counterclockwise in the positive sense, simply close contour. This is C1, and this inner boundary I am taking C2. C2 I will take in the positive sense. So, this is for the boundary I am taking into the negative sense, but when I will take this close contour C2, I will take it in the positive sense. This is including Z0, Z0 is inside. Now, you see my function 1 upon Z minus Z0. This would be not analytic only at a point Z0. So, along this part Z0 there is a circle. C analytic except at Z is equal to Z0. Now, I would use this Cauchy theorem for doubly again using the doubly connected domain. What I would get, integral along this whole boundary should be 0. So, this integral must be 0. Now, you see as I have divided it into two parts, that is the boundary as C1 and C2, I will get one interesting result. It simply says that integral of fz, that is 1 upon Z minus Z0 along this boundary C1 is same as the integral of fz, that is 1 upon Z minus Z0 along this circle C2 is same. Now, let us say this circle is centered at Z0 and it has some radius rho. So, let us see this C2 I am saying is a circle Z0 plus rho e to the power I t. T is lying between 0 to 2 pi. This is the parametric representation of a circle of radius rho centered at Z0. So, I would like to evaluate this contour integral. We do know that we can find out this integral using our basic definition of contour integration. We could the function is z 1 upon Z minus Z0. This also we would write in the parametric form, and my C2 is we are having this parametric form. So, we would write as fz t and z dash t dt, and t is ranging from 0 to 2 pi. Let us write it out. So, z dash t would be from here, because Z0 is constant, I times p e to the power rho I to the power e to the power I t. Now, evaluate this integral 1 upon Z minus Z0. From here Z is Z0 plus rho e to the power I t. So, Z minus Z0 would be rho e to the power I t, that is 1 upon rho e to the power I t, and Z dash t is I times rho e to the power I t. So, what we would get, integral 0 to 2 pi rho inverse e to the power minus I t, I times rho e to the power I t dt. Now, all these terms are getting cancelled out, giving us 1, only this I is there. So, I am getting is I is a constant, I have to integrate it from 0 to 2 pi, I would get it simply 2 pi I. This is some interesting result, you see. I was having this function 1 upon Z minus Z0, and any contour, here I have taken this contour, I had shown that this is equal to the integral along this one. Now, here I have taken this Z0, because this function is not analytic only at Z0, and I have taken a circle centered at Z0 of some arbitrary radius rho. I am getting it is 2 pi I. The integral which says is that this rho is immaterial, and now since Cauchy theorem says is that integral along the whole boundary from this multiply connected domain should be 0, that says is whatever be this outer contour C1, I can always make it equal to the integral along this inner contour C2. What it says is that if it is not this one, it is any other close contour, still I would get the integral of 1 upon Z minus Z0 as 2 pi I. That is very interesting result. You see is that how we are going to use it. So, now we are coming to our Cauchy integral formula. You see there we would be using this result, and this is really very important and interesting result. So, the Cauchy integral formula. I am writing it as in the form of theorem. Let a function f is analytic within and on a simple closed contour C, and if z naught is any point interior to C, then f of z naught is 1 upon 2 pi I integral along the closed contour C of f z upon z minus z naught dz. What it is saying is, my function f is analytic within and on a simple closed contour C. That is, on the contour C it is analytic, as well as interior to the C this function is analytic, and z naught is an interior point of this C. Then what we are saying is that the function at z naught is being determined through the function along this curve C, or this is what result it is saying. This is known as Cauchy integral formula. Now, you see is this is as I said, is this is helpful in calculating the integrals, evaluation of the integrals, as well as it is helpful in proving many results. So, proving the theoretical results, we do use this formula as Cauchy integral formula. For evaluation of integral, we could rewrite this, you see, as integral along the closed contour C of f z upon z minus z naught dz is 2 pi I times f of z naught. Now, you see what it is giving. It is not anything new, we are starting with that f is analytic. F is analytic, all right, but when we are writing is f upon z minus z naught, and z naught is interior to the C. So, certainly we are not having the function f z upon z minus z naught analytic on the complete domain, because Cauchy integral theorem says is simply connected domain, the function has to be analytic in the whole of the domain. Now, we are not having, we are having at one point z naught, we are having that the function is not analytic. If it would have been analytic at that point also, then we do know along any simple closed contour C it should have been 0, but it is not. So, what we are saying is that is we are having is it is this integral is equal to this. So, if I do have in a simply connected domain, let us say a function which is analytic only at one particular point, then integral can be obtained as that particular point, the function value at that particular point into 2 pi I. So, you see that is what is the consequences of this result and how we are using it. Before moving to that, let us first find out this formula. That is why I have written it in the form of theorem and proof. So, proof means is finding of this formula. So, let us move to the proof of this result. For proving this, we would use multiply connected domain in Cauchy integral theorem. So, let us say this is a closed contour C, and this is point z naught which is interior to this contour C, and I do have a circle centered at z naught, this circle C naught, and this is again positively oriented. This contour C is also positively oriented. So, let us start with this one. F z is analytic in this whole region. That says is f z would be continuous. If f z is continuous, by definition of continuity, we do know that f z minus z naught, because function is analytic everywhere. So, function is analytic at z naught also. It is analytic at z naught means it is continuous at z naught. Continuous at z naught, that says is if I take any small neighborhood of z naught, the difference between the function would always be made arbitrarily small. So, that is what we are writing by the definition of continuity, that f z minus f z naught would be less than epsilon for all z lying in a delta neighborhood of z naught, or writing it z minus z naught is less than delta, mod of z minus z naught is less than delta. Now, let us take rho which is less than delta, and this rho I will take the radius of this circle C naught. So, now let us define a circle C naught as centered at z naught with the radius rho. So, this is the parametric form of my circle. z naught plus rho e to the power I t for t lying between 0 and 2 pi. So, let us see the function f z upon z minus z naught. F z is analytic throughout this region interior to the C. So, f z upon z minus z naught would be analytic throughout this region except at the point z naught. Now, if I take this internal circle C naught, then this take this out of this C naught, interior of C naught out of this region C, then what I would get? I would get a multiply connected or doubly connected basically domain in which this function f z upon z minus z naught is analytic. So, using this Cauchy integral theorem for doubly connected domain, I could say that integral along this complete boundary must be 0. What it says is that integral along this C minus integral along C naught, that is you do know that is if we are taking the boundary, then it should have been the negative sense. So, we are writing it minus C naught f z d z must be 0. What it says is that my integral of this boundary C along this contour C of f z upon z minus z naught d z must be same as integral along this contour C naught of f z upon z minus z naught d z. So, we have to evaluate this integral. What we are saying is we have to actually prove our formula. So, rather than evaluating this integral, what we will do is you see is that we would do that this integral must be equal to 2 pi I f z naught. So, for writing f z naught, we do write it out like this one, C times this f z naught, if I do take this z naught is here. So, f z naught, that is constant with respect to this contour C naught. So, I can write the integral of 1 upon z minus z naught along this contour C, and f z naught outside very nicely I could write it out because that is a constant. So, what now I am writing, you see, making a little bit trick you could say, but it is not actually trick, we are just proving that formula, for that we require it. What we are writing, f z d z upon z minus z naught integration along this contour C minus f of z naught integral of 1 upon z minus z naught along the contour C naught. This what from here we do know that this is equal to this. So, this is same as integral along the contour C naught of f z upon z minus z naught. If I write it out, substitute over here, what I would get, this would be equal to the integral along the contour C naught of f z minus f z naught upon z minus z naught. Now, here I would use for our favorite inequality, that is what ML inequality is. So, what we are have find it out that integral of f z d z upon z minus z naught along the contour C minus f z naught integral of 1 upon z minus z naught along the C naught is same as integral of f z minus f z naught upon z minus z naught along the contour C naught of d z. This integral, if I do see, you remember that is whatever be this radius rho, this integral we had find it out as 2 pi I. So, that is helpful, that is you are getting is that is on the left side we are having this minus 2 pi I f z naught, that is we are nearing to our the formula, and we could say that this would be equal to this formula that is 2 pi I f z naught if the right hand side integral goes to 0, because the left hand side here this integral is nothing but 2 pi I, we have already done in the example. So, this would be, if I could show that this is 0, that is this integral on the right hand side is 0, then we are done. So, let us see the right hand side integral. On C naught, z minus z naught is less than rho, because we have taken this radius as rho, and rho we have taken less than delta, if you do remember. That says is f z minus f z naught would be less than epsilon. So, now I am going to use this ML inequality on this integral. So, I am writing this complete thing. mod of C integral along the contour C of f z upon z minus d z naught dz minus 2 pi I f z naught is equal to the modulus of the integral of f z minus z f z naught upon z minus z naught along the contour C naught. Here I am going to use the Emil inequality, since f z minus f z naught is less than epsilon in whole of this contour C naught. So, I do write it out that this is less than epsilon and z minus z naught is less than rho. So, what we are getting is this whole thing is less than epsilon upon rho, and this length of this contour, that is what we are having is Emil inequality, that this is less than m and this is the length of the contour. The radius of this perimeter of this circle we do know 2 pi r is the here rho. So, this is 2 pi rho, what we have got 2 pi epsilon, and since epsilon we have taken an arbitrary small quantity and this can be made arbitrarily small, what it says is here we are talking about the absolute value, this can't be negative. We are saying is absolute value can be made as small as possible, less than a value which is as small as possible. What it says is simply that this would be 0, that this is equal to 0. Hence, by definition of this continuity, we do get that integral of f z upon z minus z naught along the contour C is nothing but 2 pi I f z naught, where z naught is interior to this point. So, we had established our Cauchy integral formula. Let us see this in other words, we could write it out this one f z naught 1 upon 2 pi I, that is rewriting it. Now, let us see that is how it is helpful in solving certain integrals. So, we just go the examples of evaluation of integrals. Evaluate this integral along the contour C of z upon 9 minus z square into z plus I, where C is the circle mod z is equal to 2, that is the C is the circle with the radius 2 centered at origin. Now, let us see how we are going to solve it. Let us first see is that is what is my contour. My contour is this, where a circle of radius 2 with center as origin. Now, let us see what is my function. The function I am considering is as z upon 9 minus z square. This function will cease to be analytic at z is equal to plus minus 3. Z is equal to plus minus 3, that would be outside your points, while as if I take the complete function, that is now that would be f z upon z plus I. Z plus I, if I do take, that is minus I point. So, this is this function is completely analytic inside and on C, but z is equal to minus I, where this whole function is not analytic. This minus I is here, you see this is 2 and this is my minus I. So, now what we have got a function f z which is analytic on a closed contour and within it, and z naught, that is minus I, is any other point which is interior to the contour C. Then integral along that contour C of f z upon z minus z naught can be given as 2 pi I f z naught. So, now we can use it. So, using this Cauchy integral formula, this integral I am writing it, the function is f z is z upon 9 minus z square, and here it is z minus of minus I. This should be 2 pi I f z naught. F z is z upon 9 minus z square at z is equal to minus I. When I keep z is equal to minus I would get is I square. So, I square is minus 1, I would get it 10, and here it is minus I. So, I am getting is 2 pi I square, that is minus I square. So, 2 pi minus I square upon 10, and minus I square is 1. So, 2 pi upon 10 or pi upon 5. You see is that how simply I could solve this integral which is looking very complex one is that function. So, I could find it out using this Cauchy integral formula, we could find out the solution of this integral. Let us see some more nice examples. Let us have this example. Integrate this function gz, which is z square plus 1 upon z square minus 1 on each of these 4 given circles. You see the 4 circles, one is this circle A, which is centered at 1 with the radius as 1, or rather you could see, you find it out, that is here all the circles are looking like that is they are unit circle if I just compare with this circle. Then there is another circle B which is a shifted ones, then there is another circle C which is a shifted towards this side, then there is another circle D. So, let us start one by one this solution. Let us first consider this circle A. This circle A is centered at 1 with radius as 1. So, this is my circle is z minus 1 is equal to 1. Now, consider this function f z as z square plus 1 upon z plus 1, because I could write it g z as z square plus 1 upon z minus 1 into z plus 1. So, I have taken the f z as z plus 1. Now, this function is analytic, because this function ceases to be analytic only at z is equal to minus 1, and z is equal to minus 1 is outside this contour A. So, on this contour A and its interior, this function is completely analytic, and the point z is equal to 1 is inside the circle. So, we do get it that interior to C. So, now I use the Cauchy integral formula gz as f z upon z minus 1. So, using this Cauchy integral formula I would get z square plus 1 upon z plus 1 divided by z minus 1, that is f z upon z minus 1 dz. This should be 2 pi I into f z naught. What is z naught? Z naught is 1 and f z is this. So, let us write it out. Z is z square plus 1 upon z plus 1 at z is equal to 1. So, evaluate it, when z is equal to 1 I would get this 1 plus 1 is 2 and this is 1 plus 1 is 2. So, this is cancelling out, I would get it 2 pi I. So, we have got along this A contour, we have got this integral of gz as 2 pi I. Let us move to this B1. B is as I said is that is looking that is all the circles have the radius 1. So, radius is 1 is all right, but the center is now is not very clear which point. So, let us say is any number k. So, the circle would be z minus k is equal to 1, and now z is equal to 1 is interior to that circle also. So, you see B is if I am taking z is equal to 1 is the interior. So, again I will break my gz in the similar manner, that is z square plus 1 upon z square minus 1, I would write it as z square plus 1 upon z plus 1, that is on that one this circle is completely analytic, because z is equal to minus 1 is still outside this point P. So, gz I would consider this one, and I would get it fz as this. So, analytic on C. So, we do get it again using the similar manner, 2 pi I z square plus 1 upon z plus 1 at z is equal to 1, that is same as 2 pi I. Now, you see here what I have done is I have used this Cauchy integral formula again. We could get it very simply, you see how. If I consider this function z square plus 1 upon z plus 1. So, till I am not considering this minus 1 point, in all this region this function would be, which is excluding this minus 1, this function would be analytic, and we are talking about any closed contour. So, integral along a closed contour of analytic function in a simply connected domain is independent of path, or along any contour this is independent of path. That says is that this integral along this B should be also same as the integral along A. You see is that is why it is not 0, because we are having is 1 is interior. So, we are using it the deformation of path or independence of path you could say, not that is closed contour, that is Cauchy integral theorem for the closed contour we are not using, rather we are using is the independence of path, and we are getting it that it should be same as 2 pi I. So, it is not astonishing, that is we are getting the same kind of thing, it has to be actually this one. And if I just go by this one, you see here I could not apply this D. Let us come one by one. So, let us now move for the C. So, this is what I was explaining you. So, now move to the C one. C is again any z minus k, that is or rather this center is somewhere on the negative side. So, let us write it z plus k something. This k is certainly different from that whatever I have taken for the B. There is some other constant, but the radius is looking is that is it is 1. So, this is 1 and minus 1 is interior to this one. So, now and plus 1 is outside. So, now you see is that is how I am going to choose my Fz. Fz I would choose such that z plus 1 I will take outside, because minus 1 is interior. So, I will take z minus minus 1, and Fz if I do take, that would be now my z square plus 1 upon z minus 1, and this would cease to be analytic only at z is equal to 1. Now, that z is equal to 1 is outside this region. So, again all the results all the conditions of Cauchy integral formula are satisfying. So, hence using this Cauchy integral formula, we do get is that integral of z square plus 1 upon z minus 1 divided by z plus 1 along this contour C must be 2 pi I f z naught. What is z naught here is minus 1 and f z is this. So, 2 pi I z f z is z square plus 1 upon z minus 1 evaluated at z is equal to minus 1. So, when I keep z is equal to minus 1, the denominator I would get minus 2, in the numerator I would get plus 2. So, I would get it minus 1. So, it is minus 2 pi I. So, now we have got that the integral along this contour C is minus 2 pi I. Now, let us see for the D. You see is that what I have said for the D. If I see the D and my function g z as z square plus 1 and z square upon z square minus 1. This function ceases to be analytic only at 2 points, at z is equal to plus 1 and minus 1. And if I see this contour D, both the points minus 1 and plus 1 are outside this contour. So, if I take this contour C and its interior, in this domain my function g z is analytic. So, using this Cauchy integral theorem in the simply connected domain, we simply get it that integral along this contour g z d z should be 0. So, what I do have is some k which is on the positive one. Again this k is a constant which is changing the values, it is not going to be the same one for all. Here the function is analytic in and on the C. So, it is using the Cauchy integral theorem, we do say is that integral along this curve D, that is C, here we are denoting this contour, is 0. So, we have done this one. Now, we can actually extend this Cauchy integral formula for multiply connected domains as well. You see how we are doing it. So, Cauchy integral formula for doubly connected domain. Let a function f is analytic in and on the boundary of a doubly connected domain and z naught is any point in D. So, what we are having is my function f, we are having a doubly connected domain D and my function is analytic throughout that domain D including the boundary, and z naught is an interior point of the domain D. Then we say f of z naught as 1 upon 2 pi I integral along the boundary C1. You see that is because we are talking about the doubly connected domain. So, we will have two boundaries. So, one boundary is C1, another boundary is C2. So, C1 fz upon z minus z naught dz plus 1 upon 2 pi I integral along the boundary C2 fz of upon z minus z naught with respect to z. You see it is a doubly connected domain. How we will obtain this formula? we could get this formula is this doubly connected domain. What we could do is we could divide it again into two simply connected domains, and in simply connected domain we will use the Cauchy integral formula and Cauchy integral theorem. Let us see how we are going to do it. So, let us find out this one. This is my doubly connected domain which we had cut into open into two simply connected domains D1 and D2, and Z2 I have taken in the domain D2. You can take Z2 anywhere, that is on the D1 or D2, or if you are getting is your Z1 is somewhere here, you can cross this a little bit different manner, so that it should be in one of the domains D1 and D2. So, let us start in the domain D1. Domain D1 my this simply connected, and if I take the boundary of this domain, I would be getting it a closed curve on a simply connected domain. So, using the Cauchy integral theorem, that should be 0. So, in the D1 using the Cauchy theorem, we would get the integral of L1 f z upon z minus z naught, because the function f z upon z minus z naught would be analytic throughout this region, because the function f z upon z minus z naught is not analytic only at the point z naught. So, this is analytic. So, along this boundary L1, then C11 and then L2 and then this C12, this should be 0. In domain D2 I would use the Cauchy integral theorem or this Cauchy integral formula. I will take the direction as again from this side on the boundary, that is from L2 side, negative of the L2 side. So, minus L2 of f z upon z minus z naught dz plus C2, that is you will get it C21 actually, the C12, that is this is C12, and then minus of L1 and then C22. This is a simply connected domain, z naught is interior to this closed contour. So, using the Cauchy integral formula, it should be 2 pi I f z naught. Now, add these two. If I do add, you find it out that the integral along this L1 and minus L1, the integrand is same f z upon z minus z naught, and it is analytic on this whole region L1. So, it is just the sense reversal one, and we do get it as that it is 0. Similarly, with the L2 and minus L2 it would be 0. When we are talking about C11 and C12, they are in the same orientation. So, they should add it up, and similarly C21 and C22, they would also add up in this orientation. So, that should be minus C2. So, what I do get is C1 f z z minus z naught dz plus C2 f z z minus z naught dz is equal to 2 pi I f z naught, and that gives me the formula that f z naught is 1 upon 2 pi I integral along the boundary C1 of f z upon z minus z naught plus 1 upon 2 pi I integral along the boundary C2 of f z upon z minus z naught. So, similarly we could, if you do have a more p connected domain, you can extend this formula, and this can be used for finding out the integral, that is evaluation of integral. Examples I am not doing over here, I am leaving it for you to do this kind of examples. You have now learned, that is Cauchy integral formula we had learned, that is how to obtain it, and we had also learned to use it in evaluation of many integrals. So, today we would I would finish up my lecture over here, but as I said is this Cauchy integral formula is very crucial or playing very main role in proving certain results of analysis. So, next lecture we would go with those things. So, today we had learned, that is an important consequence of Cauchy integral theorem as the Cauchy integral formula and its use in evaluation of many integrals. That is all for today. Thank you.